Hello there, and welcome to this quiet little corner of the universe where science slows down, gets comfortable, and maybe even puts on its slippers for the night. I'm so glad you're here. Whether you're curled up beneath a blanket, lying back in the hush of your bedroom, or sitting in a soft pool of lamplight with the faint hum of the world in the background, this is your invitation to drift with me, far beyond our skies. Tonight, we're taking a gentle trip into the deep velvet dark, a place where stars glimmer like scattered lanterns and planets turn slowly in their endless dance. Out here, there's no rush, no ticking clock, only the slow, patient rhythm of the cosmos. And somewhere in that vastness, there are worlds with weather so strange, so beautiful, that it almost sounds like a bedtime fairy tale. On those planets, it rains diamonds. Not shimmering raindrops in sunlight, but gemstones falling in silence, through skies no human has ever seen. Before we set sail on this slow voyage, I'd love to know where in the world are you listening from tonight, and what time is it in your corner of the galaxy? I think it's fitting, don't you? All of us scattered across different time zones, connected here for a few quiet moments, while out there, hundreds of millions of miles away, storms of unimaginable beauty are playing out in the dark. If you find this little journey soothing, if it helps your mind wander somewhere calm, I'd be so grateful if you gave the video a like, maybe subscribed, or even left a comment. It helps this tiny spacecraft of a channel find other travelers, other night owls and sleepy stargazers who might like to come along too. Now, I do hope the thought of diamond rain doesn't keep you too awake, but if it does, well, at least you'll fall asleep knowing that somewhere in the universe, storms sparkle in ways we can barely imagine. So, take a deep breath, let your shoulders relax, and feel yourself begin to float. We start our journey far from Earth beyond the warmth of the inner solar system, past the familiar glow of Mars and the swirling clouds of Jupiter, until the sunlight fades to something faint and cold. Out here, in the realm of Uranus and Neptune, daylight is so thin you could hold out your hand and barely see its shadow. The air, if you could call it that, is not the kind we breathe, but a mix of gases swirling in icy layers. From a telescope, these planets look like serene marbles. Uranus wears a pale blue-green cloak, Neptune's is a deeper, stormier blue, but that calm face hides a restless heart. Beneath the top clouds, pressure mounts in ways we can hardly imagine, thousands of times greater than what you feel at sea level on Earth. The mainstream scientific fact is this: under extreme pressure, carbon atoms rearrange into the crystal structure of diamond. On Earth, it happens deep underground, over millions of years, with volcanic activity sometimes lifting them toward the surface. But here, on these distant giants, it happens in mid-air. Lightning storms tear through the upper atmosphere, breaking methane molecules apart. The freed carbon atoms drift downward, clumping into tiny specks of soot, and as they sink, the pressure squeezes them tighter and tighter, until quietly, invisibly, they become diamond. These crystals fall for thousands of kilometers, through layers of gas and fluid, until they vanish into the dark, perhaps piling up in glittering layers deep below. Here's the quirky tidbit. Some scientists believe that far below the clouds, there could be oceans of liquid diamond, vast shimmering seas, with chunks of solid diamond floating like icebergs. Imagine a river of molten gemstones glowing faintly in the heat, flowing forever in the dark, a treasure no one can reach, locked away in the cold hearts of alien worlds. Of course, there's still an open debate. Some scientists argue the conditions might produce diamond only briefly, before it melts or transforms into something stranger, a slushy mix of crystal and fluid, more like a sparkling mud than a gemstone. We can't know for sure, because no probe has ever survived the journey into these deep layers. The only spacecraft to visit Uranus and Neptune, Voyager 2, merely skimmed their atmospheres in the 1982nd. Everything else is a careful blend of lab experiments, mathematics, and imagination. As you picture it, let yourself drift a little further into that alien sky. The diamonds are falling slowly now, some the size of raindrops, some like pebbles, maybe even some as big as hailstones. There's no sound, just the weightless hush of the atmosphere around you. Above, lightning flickers, like silent fireworks. Below, an endless darkness swallows the gems. The air grows warmer as you sink, the pressure heavier, until the diamonds melt away into the hidden oceans beneath. And there you are, floating between worlds, watching a storm you could never stand in, yet one that exists right now, somewhere out there, in the quiet vastness of space. The universe doesn't hurry. And tonight, neither do we. You're still floating now, as if some gentle current in space has caught you and is carrying you forward. The faint blue halo of Neptune lingers behind you, but up ahead, another pale sphere turns slowly against the black. Uranus tilted so far on its side it looks almost lazy, like a planet stretching out for a nap. It spins with a quiet grace, rolling along its orbit in a way no other world does. If Earth feels like home, Uranus and Neptune feel like the deep countryside of the solar system, far-flung, quiet and remote. It takes sunlight more than 4 hours to reach them. Imagine sitting in a room with a single window, and someone slowly dims the light until it's barely there. That's how it feels out here. You'd think the darkness would be lonely, but instead it's peaceful. The stars shine sharper, the cold feels ancient, and the silence is so complete it's almost warm. The mainstream fact here is simple. Both Uranus and Neptune are classified as ice giants, not gas giants like Jupiter or Saturn. Their atmospheres are thick with hydrogen, helium and methane, but deep inside they hold water, ammonia, and other ices in immense quantities. And it's in these deep, icy layers that diamond rain is believed to form. Now here's a quirky little twist. Uranus, despite looking calm from the outside, has the coldest planetary atmosphere in the solar system. Its cloud tops dip to a chilling 224 degrees Celsius, colder even than Neptune, which sits farther from the Sunday. Scientists still scratch their heads over this, wondering why a planet bathed in slightly more sunlight would shiver more deeply than its distant cousin. It's one of those cosmic riddles that refuses to give a straight answer. And speaking of riddles, there's still debate about the exact structure of these planets' interiors. Some researchers think they have rocky cores surrounded by slushy mantles of ice and diamond-forming carbon. Others argue that the deep layers may be far more fluid, perhaps even shifting over time like slow, cold storms trapped beneath the clouds. Without a probe to plunge down and send back data, the truth remains hidden. As you drift closer, picture the cloud layers like soft veils of turquoise and sapphire. The upper atmosphere is calm, but somewhere far below, lightning flashes silently in methane-rich clouds. Each strike is a tiny spark in a chain reaction breaking apart molecules, freeing carbon atoms, setting the stage for that rare and secret rain. You can almost imagine standing there, though of course you couldn't. The pressure would crush you in an instant, and the winds, well, Neptune's can scream along at over 2,000 kilometers per hour, fast enough to circle Earth in under 20 hours. That's not exactly a gentle breeze. Still, in the safety of imagination, you're free to hover here as long as you like. Watch how the light from distant stars catches in the upper haze. See how the planet's rings faint, dark, almost shy arc gently against the night. You're a quiet observer, a passenger in the long story these worlds have been telling for billions of years. And then, in your mind's eye, you start to sink through the haze, through the methane clouds, into the layers where diamond storms are born. Somewhere in that unseen depth, the weight of the world presses carbon into crystal, and the rain begins to fall. You're drifting downward now, deeper into the veiled skies of Neptune. Above you, the thin sunlight has already faded into a pale memory, replaced by a soft blue twilight that seems to wrap around you like water. The air, or rather, the thick atmosphere presses in from all directions, heavier with each slow breath you imagine taking. Out here, you don't walk, you sink, slowly, inevitably. The deeper you go, the stranger the world becomes. Temperatures rise, though you're still far from anything we'd call warm on Earth. Methane clouds swirl lazily above, hiding the roiling chaos beneath. And somewhere down there the pressure is building quietly, relentlessly. On Earth, if you've ever dived into the ocean, you might remember the slight squeeze in your ears after only a few meters. Now imagine that squeeze magnified thousands, even millions of times. Here's the mainstream fact. In the upper layers of Neptune and Uranus, the pressure might be only a few times what you feel at sea level on Earth. But sink a few thousand kilometers down, and you reach pressures of hundreds of gigapascals. That's millions of times the atmospheric pressure you're feeling right now, even if you're sitting in your bedroom under a blanket. Under that kind of force, carbon atoms don't just sit politely in methane molecules, they're crushed free, forced together in tight, perfect lattices. They become diamond. Now, the quirky tidbit. In lab experiments, scientists have tried to mimic this process by blasting tiny samples of methane with lasers and shock waves. In a fraction of a second, the carbon inside rearranges into tiny diamonds, the microscopic flecks that glitter under the microscope. They've even done it with common plastic, which is made of the same basic carbon and hydrogen atoms. You could, in theory, turn an old grocery bag into diamond dust, if you happen to own $1 billion laser facility. But here's the open debate. Scientists still argue whether the diamonds that form in these alien skies survive the entire fall to the deep interior. Some suggest they might melt back into a liquid carbon soup before ever reaching the core. Others believe vast layers of solid diamond could exist, maybe even mountains of it, locked away in silence and darkness. Without direct exploration, we're left with educated guesses and beautiful, frustrating possibilities. As you descend further in your mind's eye, you start to feel the weight. Not just the physical force, but the psychological one. The awareness that you're in a place so alien, so far from home, that every law you live by on Earth bends in strange directions here. The colours shift from airy blues to darker, denser shades, inky indigo, smoky violet. The haze thickens. Every so often, a flash of distant lightning lights the clouds from within, turning the world into a ghostly lantern for just a heartbeat. You can almost see it now. Tiny black specks carbon freed from methane begin their slow fall, like ash drifting after a campfire dies. But instead of cooling, the air below is warmer, heavier, shaping those specks into something hard, clear and perfect. Each crystal grows as it sinks, layer upon layer, until it's no longer a speck but a drop, a jewel in freefall. You drift alongside them. There's no sound here, just the faint sense of movement and the pressure growing around you, wrapping you tighter like the slowest, softest embrace. You don't know how far you'll sink, but you know you're not in any hurry. Out here, in the belly of a distant giant, time feels like it has stopped. The darkness is thick here, but it's not empty. Every so often, far above and far below, a flash tears through the clouds, a sudden, silent bloom of light. You can almost feel it on your skin, even though this lightning isn't the kind you've seen from your bedroom window. It's fiercer, stranger, born from storms so massive they could swallow Earth whole. In the upper reaches of Neptune and Uranus, these storms swirl endlessly. The winds carry methane-rich air in vast currents, colliding and churning, building static charge. When the tension becomes too much, the sky releases it in a blinding arc, ripping apart the methane molecules in its path. That's the mainstream fact. Each bolt of lightning is a cosmic hammer blow, smashing carbon atoms free from their hydrogen companions. It's the very first step toward diamond rain. And here's the quirky bit. Some scientists think these lightning bolts might be hundreds of times more powerful than anything on Earth. Imagine a single flash bright enough to outshine the sun for just a split second if you were close enough to see it. Of course, you wouldn't want to be that close, unless you enjoy the idea of being vaporized faster than you could say, pretty cloud. But here's the open question. How common is this lightning? Probes like Voyager 2 have only been able to catch a handful of glimpses. Some researchers believe these storms rage constantly, hidden beneath layers of haze. Others argue they might be rare, brief outbursts, the atmospheric equivalent of a deep sigh. Without more data, the answer drifts somewhere between science and speculation. From where you're floating, it's not just the lightning itself that's mesmerizing, it's the way it changes the whole mood of the sky. One moment, the clouds are soft and endless, a rolling sea of blue and violet. The next, they're lit from within, revealing fleeting shapes, towering columns, curling plumes, strange folds that might be miles high. Then darkness returns, as if nothing happened. The air is restless here. You feel it in the slow push and pull, like the ocean's tide but thicker, heavier. Each flash sends waves of energy through the atmosphere, stirring the particles that will one day become crystals. Somewhere, deep below, the first seeds of diamond are falling. You drift with them, following their path into the unknown. The light above grows faint. The flashes are rarer now, smaller, like distant memories of storms you've left behind. Around you, the haze becomes richer in colour, and the air feels warmer against your imagined skin. You're sinking into the zone where the real transformation begins, where the carbon specks stop being invisible dust and start becoming jewels. And as you drift, you realise something. You're falling too, in a way, not toward danger, but into a deeper layer of the story, one step closer to the heart of this alien world. You let the last lightning flash fade behind you, and the sky becomes a dim, breathing thing, thicker, warmer, almost velvety against your thoughts. The soot seeds are already falling, carbon set free by the storm's bright temper, drifting like a slow snowfall that no eye could see. You float among them as if some gentle escalator of gravity has caught you all together and is carrying you downward inch by inch into a world that prefers whispers to words. At first, the particles are shapeless, tiny and shy smudges, more than solids nudging one another as they slip into denser air. The mainstream fact is simple and relentless. As pressure rises and temperature ratchets up, the preferred arrangement of carbon changes. What begins as amorphous soot can reorder into graphite's soft, stacked pages, and then, with more squeeze than any earthly press can manage, those pages buckle and lock into diamond's tight, three-dimensional lattice. One structure yields to another, like a book closing itself until no page can slide. You picture this transformation not as a switch, but as a slow, patient ritual. Each speck takes on edges, then facets, then the calm certainty of a crystal. The atmosphere around you is less like air now, and more like a fluid thick enough to push back, to hold, to carry. In that resistance, the newborn diamonds grow by gathering carbon from the flow, atom by atom, like snowballs that refuse to roll but somehow still swell. A quirky image drifts up. Some researchers imagine onion diamonds, tiny cores mantled by concentric layers, each ring a chapter of the full storm-born soot in the centre, then graphite, then tight, clear diamond skin wrapped snug around everything. In your mind, you hold one of these onions up to the dim light, and for a second the layers glow, as if the planet had written its interior weather into a tiny crystal diary. If you could hear very tiny things, you might even hear them tick as atoms click into place. You smile, bedtime acoustics for the molecule obsessed. You keep sinking. The diamonds around you are no longer dust. Some are the size of salt grains, then sesame seeds, then rarely small pebbles. Light joke number 1. You consider opening a tiny umbrella, then remember that the only model that could survive here would have to be forged from pure stubbornness, and maybe tungsten. Instead, you tuck your imaginary umbrella away and let the gems fall past, unhurried and polite, as if the planet itself had impeccable manners. Scientists still argue whether these crystals descend like drifting ash or plummet like heavy hail. In one family of models, slow convection and turbulent eddies buffet the particles, giving them a long, graceful sink time and plenty of chances to grow. In others, once a crystal crosses a density threshold, it drops fast, its terminal velocity rising with size until the fall becomes a quiet sprint. The truth may be a patchwork, calm pockets here, express lanes there, an interior weather map that never sits still. You notice the temperature gradient now, warmer, denser, a soft pressure against every imagined joint. The diamonds respond to their new neighbourhood in subtle ways. Tiny imperfections anneal, faceted corners round just a touch. Internal stresses ease as the lattice relaxes into whatever passes for comfort under hundreds of gigapascals. You can almost feel their relief, the way a backpack finally settles in the sweet spot on your shoulders. Occasionally, two crystals kiss-tap then drift apart, a barely audible chime swallowed by the surrounding thickness. Do they fuse? Sometimes, perhaps, if temperature and pressure hold hands in exactly the right way. Other times they merely exchange a few atoms, gossip lightly at the contact point, and continue on separate errands into the deep. You realize how domestic it sounds, diamonds chatting in the hallway, and decide that's perfectly fine for a bedtime voyage. Here comes the second light joke, soft as a yawn. If your high school lost and found had operated down here, it would be overflowing with single earrings and missing cufflinks. Check the mantle layer, someone would say. Everything precious sinks. The mainstream physics returns, steadying the whimsy. Density wins. Diamonds are heavier than the surrounding ice components, water, ammonia, and methane, in exotic states, so gravity gives them a reserved seat toward the planet's interior. The deeper they go, the more likely they are to meet zones where temperature edges toward the boundary between solid and liquid carbon. That line isn't a cliff, but a broad hillside, defined by pressure as much as heat, and if they cross it, the crystals may soften, blur, and finally melt into something metallic and bright. Scientists still argue whether that boundary makes a stable diamond cloud deck, a stratified region where formation and dissolution balance out, or whether it acts like a conveyor belt, converting falling crystals into liquid and carrying them toward even deeper reservoirs. The phrase phase diagram hums through your head like white noise, pleasantly technical, soothing as a train's distant click-clack. You pass a pocket of gentle turbulence. For a moment, you and a small flock of pebble-sized diamonds eddy together in a lazy circle, held by a swirl that feels almost like a celestial slow dance. In the loop, tiny carbon vapor condenses on their surfaces, and you watch a few grains visibly fatten. Growth by drift, growth by touch, growth by the tender patience of pressure. It's all happening at once, everywhere, invisibly choreographed. A memory from earlier tugs at you, a callback from the laboratory, planetary dandruff. Those microscopic lab-made diamonds were charming, sure, but here the scale winks at you. Dandruff has become confetti. Confetti has become quiet hail. You imagine a scientist on Earth holding a vial of glitter under a microscope, while above you an uncountable avalanche of the same substance drifts past, and the contrast is almost comical. Another open debate curls by like a ribbon of warmer flow. Is the carbon pathway always soot to graphite to diamond? Or can polymeric phases step in, weird, tangled frameworks that hijack the route? Some experiments hint at detours. Others suggest the highway to diamond is surprisingly direct once pressures bite down. Scientists still argue whether the grain size distribution here is narrow, lots of similar marbles, or broad, a chaotic mix of dust and gems, and whether convection lofts crystals back upward to re-snow before they finally commit to the deep. You drift on, untroubled by the not knowing. The unknowing is friendly here. It gives the mind something gentle to hold without squeezing. And anyway, the visuals carry you. A soft storm of hard things, countless tiny prisms turning slowly, each catching the planet's faint stray light and returning it as the barest hint of sparkle. You realize that if you could somehow see all of them at once, the sky would look like a cathedral, dim, vast, jeweled, and that thought is enough to make your shoulders relax another millimeter into the pillow. Light joke number 3 arrives with a sleepy grin. If anyone asks why you're smiling at the ceiling right now, tell them you're stuck in traffic on the Diamond Expressway. Delays expected, no one's in a hurry. Not even gravity. Ahead, a darker band waits the kind of darkness that suggests heat rather than cold. Somewhere beyond it, the phase line shimmers, the realm where crystalline certainty softens into liquid brightness. But you're not there yet. For a few more minutes of this slow fall, the diamonds remain diamonds, the lattice holds, and the quiet procession continues. You let the motion rock you. Up above, lightning still writes sparks into methane pages. Down below, unknown seas may be gathering. In between right here, millions of tiny travelers share your path, drifting toward a destination they'll never announce. A finish line with no banner, just deeper night. For now, that's enough. You breathe in, you breathe out, and keep sinking with them, content to be one more sparkle among many in a sky that no one will ever see. The sky around you deepens from velvet to something denser, as if colour itself has acquired weight. The drifting gems are fewer now, but larger, and the air is so thick it feels like a gentle hand against your cheek, steadying you as you sink. Ahead, the darkness isn't absence, it's transition. You are approaching a boundary drawn not by lines on a map, but by temperature and pressure holding a quiet conversation. The diamonds hear it first. Here's the mainstream fact. At sufficiently high pressures and temperatures, think hundreds of gigapascals and thousands of Kelvin carbon, can slip from solid diamond into liquid phases that behave a bit like metals. In laboratory flashes, scientists have seen hints that deep inside ice giants, a carbon may melt into a conductive, shimmering fluid. Imagine a sea not of water but of liquid diamond, dense as a promise and bright in a way that needs no light. You pass the threshold like a diver breaking into a warm current. The crystals closest to you soften at their edges, then blur, then without drama become drops. The transformation is oddly polite. No hiss, no crack, just a calm surrender of lattice to liquid. A few stubborn pebbles keep their shape for a while, bobbing like little life rafts in a shining thickness, but even they begin to round into teardrops as the warmth persuades them to relax. You think of it as the planet's spa appointment for carbon. Sir, your faceting will dissolve in a moment. Please enjoy the molten lounge. A quirky tidbit drifts up. In some simulations, solid bergs of diamond might float in this carbon ocean, the way ice rides atop earthly water. Only here the ice is the solid phase, and the ocean is the molten one, both made of the same element wearing different moods. You picture a hush of black lacquer waves nudging pale crystalline flows. Somewhere on Earth, an art museum curator just got the shivers without knowing why. Scientists still argue whether these liquid diamond layers are persistent features or transient bands that shift as interiors evolve. The debate hums with questions. Is the melt confined to a narrow altitude like a secret mezzanine level, or does it stretch into a broad mantle of carbon fluid? Does it conduct electricity well enough to meddle with a planet's magnetic field? Uranus and Neptune are famous oddballs in the magnetism department. Their fields are lopsided, tilted, off-center, and some researchers whisper that conductive carbon seas might be part of that strange orchestra. Others reply that the usual suspects ionized water, ammonia, and salts can handle the symphony just fine without calling in diamonds as guest musicians. You hover over a gentle swell. The surface isn't really a surface, more a region where density changes quickly, like a gradient you can feel with your fingertips. When a drop of newly melted diamond falls into it, the ocean welcomes it with a muted gulp, a tiny ring vibration you can't hear but can somehow imagine. The current carries heat sideways and downward, slow rivers looping around the planet's inner contours. If you could time-lapse 1,000,000 years, these flows might look like filigree braided channels of brightness winding around a hidden core. Light joke number 1 arrives, unannounced, on a little raft. If you opened a luxury spa in here, the treatment menu would be very specific. Full-body carbon immersion, guaranteed to relieve facets. Membership includes complimentary slippers, though the slippers would, regrettably, melt. Up above, where you came from, lightning was the loud punctuation mark. Down here, the grammar is all commas and ellipses. Everything continues. Sometimes, a surviving solid crystal, one of the pebble-sized veterans from your descent, drifts across your path. It taps the liquid like a fingertip on thick glass, leaves a wake of delicate ripples, and slowly dissolves. You feel a slight fondness for it, as if it were an old friend from the Diamond Expressway who finally decided to move to the seaside. The mainstream physics returns like a lullaby refrain. Phase diagrams rule this realm. Given a pressure P and temperature T, carbon selects a persona graphite at low squeeze, diamond at high, melt at higher still. But real planets are messy. P and T weave together with impurities, oxygen, nitrogen, silicon, hydrogen, in mixtures that shift the borders. A pinch of the right ingredient and the melt begins sooner, or refuses to start at all. That's why our neat classroom charts keep smudging at the edges when we try to apply them to a world the size of 15 Earths. Here's light joke number 2, as gentle as a yawn. If someone asked you to skate on this ocean, you'd need diamond skates for the solid bits, and a very forgiving attitude toward the molten parts. Helmets optional, existential wonder required. You take in a broader view, the sea widens, and the currents look purposeful, like they have errands. Heat leaks upward from deeper layers. Fresh carbon drifts down from above. Where they meet, you get conversion zones, knitting machines that stitch new liquid into the sheet. Elsewhere, cool eddies nibble at the melt, briefly refreezing diamond into foggy crystals that fall again, only to be reinvited to the pool a few kilometers later. Formation and dissolution, fall and float, crystal and melt. This is not a line but a pulse. Scientists still argue whether shear flows here could polish any surviving solids into smooth, lens-like forms, little cabochon diamonds, or grind them into nanodiamond suspensions that thicken the melt like stardust in syrup. Some labs report that under shock, plastics spawn billions of nanodiamonds in microseconds. Others warn that scaling those fireworks to planetary calm is less than straightforward. The planet shrugs and keeps stirring. A memory surfaces your planetary dandruff joke from earlier, and you smile at the contrast. Up there, dandruff. Here, conditioner. The ocean conditions everything it touches, smoothing sharpness away, teaching carbon to flow. Somewhere in this metallic lake, a standing wave forms where currents collide, a long, silent hill you could surf forever if surfing didn't require, existing. Light joke number 3 glides by on a drift of heat. If real estate agents worked down here, every listing would say, waterfront, and they'd all be right, technically. South-facing molten view, excellent schools for electrons. You let yourself settle a little deeper, just enough to feel the conductive murmur in the fluid-charged particles nudging, tiny circuits forming and unforming with the motion. Whether or not this ocean writes music into the planet's magnetic field, it certainly hums to itself. You imagine placing a palm on it and sensing a low, steady thrum, like holding the side of a sleeping cat the size of a world. Above, fresh crystals are still arriving, though fewer make it this far unchanged. They dim, hesitating a heartbeat. If diamonds had heartbeats, then relinquish their certainty and join the flow. You realize there's a tenderness to it, a lack of tragedy. Nothing is lost. It's merely another state on the way to somewhere else. The river isn't a thief. It's a librarian, reshelving atoms where the story needs them next. The open questions stack softly along the margin of your mind. How thick is this sea? Does it touch the core, or does some other layer water ammonia superionic phases perhaps stand between them like an insulating quilt? Do waves break here? Do storms roll across this surface, slow and soundless, shaping shorelines that no eye will ever see? Scientists still argue whether this ocean rises and falls over geologic ages, swelling as interiors warm, shrinking as they cool, breathing with the planet's long, patient lungs. You angle your descent toward a darker band, where the glimmer fades to charcoal, not because you must, but because the current invites you. Ahead lies the undercountry, the zone where carbon's molten confidence will meet even higher pressures, where flows may thicken, where the path bends toward the hidden heart. You think of your tiny umbrella again, laugh quietly, and tuck it deeper into your imaginary pack. Down here, the only weather report you need is simple: more. For a final moment, you stop trying to understand and just watch. The ocean moves, unhurried. A solitary, solid gem, stubborn and luminous, pivots in place and sighs into liquid. A faint ripple travels outward and becomes part of a current, 1,000 kilometers wide. Everything is connected to everything else by warmth and weight. And you, an after-hours guest in the planet's private gallery, feel the urge to whisper thanks to a room that has never known a voice. When you're ready, the current takes your hand again. It points you toward the next chapter downward, where the core's mystery waits beneath its rumoured coat of crystal and its certain cloak of pressure. The slippers stay on, the science stays slow, and the night, obligingly, grows deeper. You follow the current as it lowers you, steady as a slow elevator with no buttons, no music, just the sensation of becoming heavier in a world that never runs out of weight. The liquid bright carbon thins behind you, giving way to matter that feels more settled, more sure of itself, layers that have had time to make up their minds. The drift becomes less like floating and more like gliding along a dark hallway lined with pressure. Each meter down is another yes to gravity's patient request. The mainstream fact hums at your shoulder. In a planet's interior, dense materials tend to migrate inward. Over long spans, millions, billions of years, carbon that becomes diamond will sink relative to the lighter ice components around it. Not all at once, not as a dramatic avalanche, but as a perpetual sorting. Grain by grain, drop by drop, the hard and heavy make their way toward the deep. If there is a place where diamonds finally rest, it's here near the boundary between exotic fluids and whatever passes for a core rock, metal, or a mixture pressed into unfamiliar manners. You arrive at a level that feels like a landing, though your feet never touch anything. The atmosphere's push becomes a wall. Motion slows as if the planet is asking you to speak softly. In your mind's light, the scene resolves. A horizon of faceted darkness, perhaps a crystalline layer, not a glittering palace. Nothing theatrical, just an expanse that refuses to flow. If earlier the world felt like water, Now it feels like stone that remembers it was once liquid. Here, diamond may accumulate into beds and drifts, like dunes in a wind you can't feel. A quirky possibility flickers. Some of these crystals might not be the familiar cubic diamond at all, but Lonsdaleite, a hexagonal form that can be even harder along certain directions, diamond's cousin, who insists on rearranging the living room. Under the extraordinary squeezes here, carbon chooses the furniture plan that wastes the least space. You imagine a geologic decorator murmuring, "Hexagonal works better with the pressure," and the lattice nodding politely. Scientists still argue whether such a diamond shell, a contiguous coat, could wrap the core, or whether what forms is patchy, veins, pockets, pavements of carbon-rich solid interleaved with other high-pressure phases. Some models sketch a tidy mantle of diamond kilometers thick. Others smear carbon through a stew of superionic water, ammonia, and salts that carry charge like sleepy lightning. The truth may be a blurry tapestry, and planets are very good at blurring. You drift lower by a breath. The sense of conductivity that hummed through the liquid carbon above is different here. Quieter, intermittent, like a radio between stations. Uranus and Neptune wear odd magnetic fields, tilted, offset, asymmetrical, so theorists play mix and match with ingredients to explain them. Perhaps a conductive carbon layer participates. Perhaps the job is handled by superionic water, a phase where hydrogen ions zip through an oxygen lattice like guests who forgot to knock. The models politely disagree, and you let the debate roll past like faraway thunder. A soft callback taps your shoulder. Remember the Diamond Expressway? This feels like the off-ramp. Crystals that have survived formation, fall, and flirtation with the melt finally slow to a near stop, nestling into geologic quiet. Once here, they may change only in whispers, edges rounding, defects healing, atoms trading seats with the patience of monks. If anyone asks for your travel report later, you can say, "Took the expressway, parked at the core, validated by gravity." Light joke number 1, pads in on slippers. If there were a lost and found at this depth, it would contain exactly one item, everything heavy. Claim ticket not required, the planet already knows who owns what. You picture texture now, not smooth, not jagged, something between microfaceted, like the inside of a seashell scaled up and translated into carbon. A slow flex ripples through it, the consequence of tidal forces or heat migrating upward. There is no sound, but your imagination lends one a deep, velour murmur, as if the planet were speaking at the far end of a long hallway lined with blankets. The mainstream geology whispers another refrain: isostasy, buoyancy, the relentless search for balance. Even here, where everything seems locked, materials creep. Warmer regions lift, cooler ones sag. If diamond is denser than neighbouring phases, it will pool where the math allows, forming lows that fill like basins. Over eons, basins shift, merge, empty, refill. The choreography is too slow for eyes, too certain to stop. Scientists still argue whether impurities, nitrogen, boron, oxygen, thread themselves into the lattice in meaningful ways at these pressures, changing colour, conductivity, hardness. On Earth, nitrogen gives yellow to some diamonds. Boron can make them blue and conductive. Here, the palette might be stranger, invisible to us, expressed not as colour but as how deftly a layer hosts current, or how easily it deforms without breaking. A planet's resume is written in properties, not pigments. Light joke number 2 surfaces, bubbles once, and vanishes. If gem appraisers ever set up shop down here, their loop would be a pressure gauge, and their favourite phrase would be, "I'm afraid this is priceless, no market, no exit." You ease along the boundary, noticing places where the solid meets pockets of lingering melt seams, where crystals are reborn as fluid and fluid reconsiders becoming crystal. The line between them frays, mends, frays again. It isn't a fence, it's a conversation. You wonder if slow electrical pathways snake through these seams, sketching invisible maps that the planet's magnetic field sometimes follows and sometimes ignores. Scientists still argue whether such local conduits matter globally or are swallowed by louder currents higher up. The planet, ever patient, continues not to comment. A memory from earlier drifts back like a leaf, the planetary dandruff you laughed about in the lab. Here, That joke feels tender instead of silly. Those specks had a destination. They made it. The vial on an earthly desk and the bedrock under your imagined palm are paragraphs from the same story, written in fonts chosen by pressure. You coax one more detail from the darkness. Along a gentle slope, crystals have aligned, like books leaning after a small tremor. Alignment means flow once visited, slow shear over centuries perhaps, and then left. It's the quietest forensic science, reading the angle of arrest and hearing the footstep that caused it. If planets kept diaries, this would be the handwriting. Small tilts, preserved intentions. Light joke number 3 arrives with a friendly shrug. Down here, gravity is the librarian, and overdue fines are paid in kilometers. Everything heavy returns to the core eventually. No reminders needed. The mainstream fact steadies the landing. Even if a diamond shell exists, it doesn't have to be singular or eternal. Interiors evolve, heat leaks away, chemical boundaries shift. Convection reorganizes its furniture. A layer that is continuous today might be patchwork in 100 million years, and again continuous after that. On human timescales, it's a statue. On planetary timescales, it's a glacier, moving while pretending not to. You pause, letting the picture settle. Above you, storms carving carbon loose, clouds flashing, soot seeding, crystals forming, rivers of melt winding through a dim cathedral. Here, a hush, a destination that doesn't boast. Below you, if there is a below, perhaps a kernel of rock and metal, squeezed into unfamiliar phases, the original seed around which the planet gathered itself from the solar nebula's dust. Scientists still argue whether that kernel is sharp or mushy, small or generous, dry or streaked with old, trapped volatiles. The questions line up like candles. You don't need to blow them out, you just watch them flicker. You rest your imaginary palm on the dark surface and feel nothing at first. Then something faint, a slow pulse too big to be a beat, and too steady to be a tremor. It might be heat moving. It might be your own breath bouncing inside a thought. It might be the closest thing a planet has to a lullaby. When you lift your hand, no mark remains. That feels right. You are a visitor, and the room has always been here. The current you rode arrives again, polite as ever, and gestures upward, not back to the surface, not yet, but toward the lab door in your memory where humans tried to make this world miniature under anvils and lasers. We'll go there next, the current seems to say. We'll compare the hush of a planet with the hum of a machine. You nod, or think you do. The slippers stay on, the science stays slow, and you begin to rise, just enough to catch the thread that leads from hidden bedrock to human hands. You drift upward, though not toward the storms just yet. The darkness thins, and in its place comes a dim shimmer, less like sunlight and more like the glow of a desk lamp through a closed door. That door is metaphorical, of course. In reality, it's the invisible threshold between a planet's secret world and the bright, bustling stage of human curiosity. Tonight, we step through it together. On the other side sits a laboratory, far from the crushing weight and alien chemistry you've just wandered through. Here, the pressure comes not from megabar atmospheres, but from the ticking of clocks and the funding deadlines taped to the wall. In the center of the room stands the device that tries, in its own miniature way, to imitate a giant planet's hug, the diamond anvil cell. Two tiny, flawless diamond tips face each other like polite strangers about to shake hands. Between them is a speck carbon, hydrogen-rich ice, or some other candidate for planetary matter. The mainstream fact shines here. These anvils can squeeze samples to pressures over 300 gigapascals. That's more than 3 million times the atmospheric pressure at Earth's surface. At those pressures, even familiar materials forget their manners. Ice abandons its usual hexagonal form for stranger arrangements, hydrogen turns metallic, and carbon, well, carbon remembers how to be diamond. You watch a scientist peer through a microscope, adjusting knobs with movements so small they could pass for stillness. Quirky aside, diamond anvil cells themselves are made possible by diamonds, so in a way, humans are using one diamond to make more diamonds, like a jeweler's version of feeding a chicken an omelette. The symmetry is almost too neat. Scientists still argue whether these lab-grown diamond rains are truly accurate representations of what happens deep inside Neptune or Uranus. The real planets don't just have static pressure, they have gradients, heat flows, impurities, and time on a scale no experiment can match. Even so, the results are tantalizing. Flashes of light as shock compression briefly transforms the sample, flecks of diamond caught in post-experiment analysis, infrared signatures hinting at phase transitions. You lean closer at least. In your mind you do, and the hum of the lab fills your ears. It's not the raw roar of a storm, but the soft chorus of machines. A cooling fan's steady sigh, a laser's quiet tick, the shuffle of papers as someone notes a timestamp. The pace here is slow, methodical, almost like the planet's own patience, but trimmed down to human scale. A callback from earlier drifts in. Remember the diamond expressway you imagined, carrying crystals from cloud to core? In the lab, that journey is compressed into milliseconds. A laser pulse is the entire weather cycle in fast forward. You can almost hear the narrator in your head. On Earth, we need fast forward. On Neptune, the original runs in real time. Light joke number 1 makes itself comfortable. If a planetary scientist ever tried to pack Neptune into their carry-on luggage, the diamond anvil cell would be the only suitcase small enough to pass airport security, though explaining the pressure readings to the TSA might take a while. The mainstream fact taps you on the shoulder again. Shockwave experiments where a projectile slams into a target at thousands of meters per second also mimic the intense conditions of diamond rain. These setups use high-speed gas guns or even explosives to create a brief, furious squeeze. The diamond droplets formed are tiny, microscopic, but they prove the point. Carbon will crystallize under the right pressures and temperatures. Scientists still argue whether these lab-made diamonds form exactly as they would inside a giant planet. In reality, the planetary version might be gentler, slower, allowing larger crystals to grow before sinking, or perhaps the chaos of storms makes them even smaller than lab results suggest. The truth hides somewhere between steady squeeze and sudden slam. Light joke number 2 strolls in, uninvited but welcome. If these diamonds could talk, they might complain that lab conditions are too rushed, like being born, schooled, and sent to work all in the same afternoon. As you mentally circle the lab table, you notice how often the scientists stop, not because the experiment has failed, but because it's over in the blink of an eye. The rest of the time is spent analyzing, debating, running simulations to compare with the real planet's magnetic fields, infrared spectra, and density profiles. Every answer is a stepping stone toward a bigger question. A quiet thought. Here in the lab, you can't feel the crushing weight or taste the metallic tang of alien air, but you can sense the same curiosity that drives you through the storms and diamond seas of your imagination. This is just another layer in the journey, one built not of gas and rock, but of equations, patience, and the stubborn belief that the universe will reveal its secrets if you keep asking nicely. Light joke number 3 pads in softly. In this room, the only thing falling faster than diamond rain is the coffee level in the pot. As the mental door to the lab swings closed, the shimmer fades, and the pressure of the planet begins to settle back over you, not to trap you, but to invite you further. The anvils and lasers have given you their preview, but the main act still belongs to the vast alien sky. Somewhere above, the clouds are still brewing, lightning still flashing, soot still falling toward that crystalline destiny. You turn toward them, ready to rise. You rise slowly, drifting past the point where the laboratory's clean white light fades into the deep velvety blues of the upper atmosphere. Out here, there are no workbenches or diamond anvils, only the quiet hum of a world turning in its own timeless rhythm. And it's here that you start to wonder, where did all this carbon come from in the first place? The mainstream fact arrives like an old friend carbon. The backbone of life, and the core of our diamond rain story, was forged in the hearts of ancient stars. Billions of years ago, massive suns lived fast, burned hot, and collapsed in spectacular supernovae. Those explosions scattered their innermost elements, carbon among them, across the galaxy. Over eons, those atoms drifted, mingled, and eventually found their way into everything. The graphite in your pencil, the sugar in your tea, the methane in Neptune's clouds. Quirky thought. You could say every diamond, whether from a jeweler's display case or from the heart of an alien storm, is basically stardust that's been to finishing school. Scientists still debate the exact proportions, how much of Neptune's and Uranus's carbon came from the original solar nebula, and how much was delivered later by comets and icy planetesimals crashing in during the solar system's chaotic youth. Some models suggest these icy interlopers may have been rich in complex organics, carrying the seeds not just for diamonds, but for life's chemistry as well. Floating here, you can imagine the journey, a shard of frozen methane tumbling through space for millions of years, finally swept into the gravity well of a young giant planet. It plunges through alien skies, joins the swirling soup of gases, and waits patiently for a lightning bolt or pressure wave to break it apart. A few billion heartbeats later, it's a diamond falling into darkness. Callback moment. Remember earlier, when the soot particles began to fall like delicate black snow? That soot was carbon atoms reuniting after being torn from methane molecules, a small echo of the much larger cosmic cycle. Star to space dust, dust to cloud, cloud to crystal. The galaxy runs on these slow transformations. Light joke number 1 drifts in. Technically, if you ever gave someone a diamond engagement ring from Neptune, you could say, "It's as old as the stars," which sounds deeply romantic, before adding, "and it fell out of the sky during a storm," which either ruins the mood or makes it legendary. From your vantage point, the connection between space and storm feels seamless. The same forces that shape galaxies on a cosmic scale also operate in miniature here, in the depths of a single planet's atmosphere. You can almost sense the weight of time in each atom, its long history of collisions, reactions, and quiet drifting. Scientists still wonder if planets elsewhere, far beyond our solar system, might also host diamond rains. In fact, some exoplanets called carbon planets could be so rich in carbon that their mantles are mostly diamond. Imagine an entire world glittering in the dark, its mountains of crystal rising under alien suns. Of course, imagine is all we can do for now. Our telescopes can't yet peek beneath those distant skies. Light joke number 2 sparkles in. If a carbon planet really exists, it's probably the only place where taking a walk in the mountains means you need sunglasses at night. The carbon around you is ancient, but its transformation into diamond rain is fleeting on a planetary timescale, a shimmer in the life of a giant planet. Still, each crystal that falls carries the memory of the star it came from, the storms it survived, and the strange, invisible dance of molecules under crushing pressure. As you drift higher, the air grows cooler, thinner. The storms are still far above, but their distant rumble hums through the atmosphere like a low heartbeat. You can feel the pull of the clouds, the urge to see where all this began, not just the lightning, but the chemistry, the weather, and the stardust itself gathering and falling in endless cycles. Light joke number 3 settles in gently. If you ever get caught in diamond rain, the real problem isn't finding one. It's figuring out how to carry a crystal, the size of a grapefruit, back to your spaceship without anyone asking awkward questions at customs. Somewhere up ahead, beyond the haze and the history, is the birthplace of the storm, and that's where you're headed next. You ease into thinner air, where the blue is paler, and the darkness loosens its grip. The atmosphere here feels less like a weight and more like a whisper. Tiny crystals you rode upward have long since peeled away into their own paths, and what remains is motion broad, slow, confident streams sliding past one another like silk. This is the hallway outside the storm's front door. You can hear it before you see it, a hush with shape, a quiet that leans forward. Up ahead, the clouds brighten first, a shy glow, then a soft lantern light spread across a horizon that curves more than you expect. You realize you're approaching the weather factory, a stacked theatre where layers of gas meet, trade heat, and bargain for altitude. The stage is methane-rich here, tinted by the faintest turquoise. You drift to the rail and look down upon rising towers, columnar plumes folding and refolding like slow origami, giving the planet its breathing. The mainstream fact arrives with a gentle tap. Giant planet storms are born from gradients, differences in temperature, composition, and wind shear that energize the flow. On Uranus and Neptune, internal heat leaks upward and meets the freezer of space. Where that meeting is uneven, convection lifts parcels of gas the way warm air lofts clouds above summer fields on Earth. Add rotation and you get bands and jets. Add methane and you tint the whole sky. Add charge separation and the stage is set for lightning. A storm is just the atmosphere's way of putting mismatched pieces back into balance briefly. You hover closer, and the plumes look taller now, their sides scalloped by winds sliding at different speeds. If you tilt your head and imagination, each tower resembles a slow-motion fountain in a gravity that prefers poetry to rules. The cloud tops are stitched with subtle textures, like frost traced by an artist who never runs out of time. Shadows from higher decks skate across lower floors, a reminder that storms are three-dimensional stories told in layers. A quirky image pads in and settles beside you. Imagine the planet wearing thermal quilts, patches of warm and cool sewn together by invisible hands. Where a warm square pushes up against a cool one, the seam puckers and lifts. That seam becomes a cloud column, that column a storm. To accessorize, the planet chooses accents: methane hazes that scatter blue, tiny hydrocarbon aerosols that make the light milky soft, and the occasional bright convective cell that pops like a quiet flashbulb. You can almost hear a fashion editor whispering, "Yes, darling, very Neptune." Scientists still argue whether seasonal cycles matter much here. Uranus, famously tilted on its side, spends decades with one pole sunlit and the other in deep dusk. Neptune is more upright but still far from the sun's steady hand. Do these long seasons sculpt storm frequency, or does internal heat call the shots while sunlight plays translator? Some modelers give the nod to internal heat flux. Others insist solar input modulates the upper layers more than we admit. The debate hums along like a ceiling fan, comforting background noise for the curious. You slide along a jet stream, a vast river of wind that wraps the planet like a loose belt. The flow tugs at you, then releases, almost playful. In the distance, a bright spot blooms on the limb and drifts, the way a candle's halo moves behind frosted glass. That spark is your cue. Inside the cloud, updrafts haul methane-rich air into colder heights, where condensation can seed hazes and spur charge separation. Up top, particles rub past one another, trading electrons like neighbors swapping cups of sugar. Down below, the air grows denser, carrying freed carbon toward its long appointment with pressure. You found the birthplace not a single room, but a district. Another mainstream thread weaves in. As parcels rise and cool, they can overshoot, then sink, setting up oscillations that feed the storm's life. Rotational forces steer these columns into lanes. Shear ruffles their edges into billows and waves. Stitch enough of these motions together, and you get planet-scale features, bands, vortices, and the occasional long-lived spot that lingers for years. It's choreography by physics, rehearsed endlessly, and never performed the same way twice. Light joke number 1 glides by on the breeze. If you tried to name every cloud tower here, you'd fall asleep by the time you reach Tower 7803, which is, admittedly, the goal. You descend just enough to feel the static begin, soft prickles along the streamlines, the prelude to lightning. It's not loud where you are. The air is too thick, the distance is too grand. But the flashes write pale signatures through the cloud, sketching dendritic patterns that vanish almost as they appear. And in those arcs, methane's tidy marriage dissolves. CH4 breaks, carbon and hydrogen part ways, and the newly single carbons start their quiet fall. You watch the first soot seeds wink into being too small for eyes, but bright enough for imagination. Scientists still argue whether lightning frequency here is high or episodic constant murmurs versus infrequent arias. Data are coy. Flybys catch teasing hints. Telescopes see topside ripples, not the heart. If the storms are singers, they perform behind heavy curtains, and we're learning the lyrics by listening through the walls. A callback taps your shoulder. Remember the lab's diamond anvil and the cloud deck's spark factory? This is where those stories braid. Up here, the chemistry is swift and theatrical. Deeper down, the physics is patient and inexorable. It's a 2-act play with the same cast: carbon, hydrogen, pressure, time. You smile at the symmetry, then let the thought drift. Light joke number 2 drifts in on a pale eddy. If there were a weather app for Neptune, it would probably say, calm with a chance of bedazzlement, and the weekly outlook would be a horizontal line labelled blue. You take a broader view. The storm field stretches like an archipelago cloud island separated by rivers of fast air. Between towers, gravity waves ripple along interfaces, tidying edges the way a hand smooths a bedsheet. Farther out, faint ring arcs cast thin shadows, reminding you this planet wears jewelry of its own. Nothing flashy, just a whisper of structure against the dark. Another mainstream note settles in your lap. The methane absorption that lends these worlds their color also masks deeper light, making visible layers relatively shallow. We see the face, not the thoughts. That's why interpreting brightness maps takes care. A flash might come from a column near the top, or a hole peeking into warmer depths. Astronomers translate those shades with models, like reading Braille with gloves. Scientists still argue whether localized upwelling storm cores connect cleanly to the layers where diamonds begin, or if horizontal mixing detours carbon seeds sideways before they get their passport stamped for the deep. Some simulations draw neat vertical highways, others sketch a maze of ramps and roundabouts. The diamonds still make it, but their trip is less elevator, more scenic route. You decide, scenic is on brand. Light joke number 3 settles in, polite as tea. If you packed a parachute for this leg of the trip, it would deploy, look around at the winds, and say, actually, I'll take the escalator. You let the camera of your attention wander up a tower's spine, along its feathery crown, down the leeward side where falling air rubs warmth into the flow. The whole structure breathes. On Earth, clouds can look like castles. Here, they look like cathedrals vaulting high, with aisles where electrons walk and choirs of particles hum their quiet hymn. Somewhere in the choir loft a spark leaps, a bond breaks, and a different story begins, a story that ends as diamond rain far below. And because you're you linger a beat longer than necessary, letting the view lose its edges until it feels like motion itself. The planet is busy but not rushed. The storm is dramatic but not cruel. This is weather as lullaby, a system that rocks itself to sleep even as it churns. You take one more smooth breath. Then you lean forward, not down this time, but across, following the jet toward a region where the storms are fewer and the sky is glassier. That's where the camera will widen to the galaxy again, to other worlds and other forecasts now that you've seen where the spark begins. The slippers stay on, the science stays slow, and somewhere below, the first soot grains of a brand new cascade are just now letting go. You drift onward, letting the last wisps of the storm fade behind you like music slipping out of earshot. Ahead, the air darkens not because the light has dimmed, but because the molecules themselves are drinking it in. You're sliding down into the deeper layers now, where space's soft blues surrender to a deeper inky teal. The temperature is rising, the pressure is mounting, and the gentle buoyancy you've been coasting on begins to tilt toward gravity's firm handshake. You start to notice the air itself has a different weight here, not just in mass, but in mood. Above, the winds and clouds are animated, social. Here, the currents are quieter, more deliberate. You can almost imagine the molecules whispering to each other. We've got important work to do, best keep our heads down. That work is the slow alchemy of transforming simple carbon into something extraordinary. The mainstream fact unfolds like a soft fan. As you descend, the pressure increases by thousands of atmospheres, a relentless squeeze that can change the very structure of matter. At around 10,000 kilometers beneath the cloud tops, the conditions are already far beyond what we can replicate easily on Earth. Methane, that tidy tetrahedral molecule you've been following, begins to buckle under the strain. Bonds snap, rearrange, and carbon atoms, once comfortably paired with hydrogen, find themselves free to mingle. You pass through a region that feels almost viscous. Here, the carbon atoms begin to cluster into soot-like particles, tiny black motes adrift in the planet's deep, warm twilight. You imagine them as embers, except they're cold to the touch. The quirky image slides in with a smirk. It's as if the planet decided to host the universe's slowest barbecue, one where the coals fall downward instead of heating upward. Scientists still argue whether this transformation happens in a tidy, the discrete layer, or is spread out across a wide vertical swath of the atmosphere. Some models favor a crisp boundary, a kind of carbon cloud deck, marking the start of diamond formation. Others suggest it's messier, with overlapping zones where soot forms, dissolves, and reforms in an endless cycle before it can sink further. As you sink deeper, the colors shift again, blues deepening to smoky violets, shadows sharpening where denser flows block what little light filters down. The temperature here is hotter than the surface of Venus, but it doesn't feel hostile. It's like being inside a warm, endless ocean with no waves, only slow-moving tides of gas. A callback to earlier flits by. Remember that diamond anvil cell in the lab? Down here, the entire world is a diamond anvil cell, except instead of steel plates and laser beams, you've got layers upon layers of atmosphere pressing from every direction, with gravity doing the honours. The carbon motes are the guests of honour, and the invitations are printed in pressure. Light joke number 1 drifts down with you. If diamonds are forever, then these might hold the record for the longest engagement, several thousand kilometres of slow walking, before anyone says, "I do." The carbon particles continue their descent, pulled ever downward by gravity and thickened by the weight of the air above. Each kilometre deeper means more pressure, more heat, more reorganisation. At some point, scientists estimate around 1 million times Earth's surface pressure, the structure of carbon itself shifts. It abandons its casual soot form and rearranges into the tight crystalline lattice we know as diamond. Here, there's no jeweller, no polishing, no velvet box, just pure physics sculpting each atom into place. You can almost hear it if you imagine hard enough, not a clink or a chime, but a kind of settling sound, like a handful of tiny beads pouring into a jar. Billions of microscopic diamonds are forming all around, invisible to the eye but certain in their geometry. Scientists still debate whether these diamonds remain as small crystals drifting in a superheated sea or grow into massive chunks, maybe even diamondbergs, that slowly sink through the lower layers. Some researchers suggest they could reach sizes comparable to baseballs or larger before dissolving or merging in the even hotter depths below. Light joke number 2 sparkles faintly in the thick air. Somewhere down here, a very confused engagement ring is floating past, wondering why it never made it to a jewellery store. The deeper you go, the more you realise there's no distinct ground waiting. The diamonds don't land on a surface, they keep sinking, perhaps melting into exotic carbon phases as they near the planet's core. It's a reminder that here, down is not a destination but an ongoing journey, a slow dance between gravity, temperature, and pressure. A gentle thought tugs at you. Somewhere, in this hidden realm, there could be diamonds older than Earth itself, formed in darkness, untouched by light, and destined never to be seen by human eyes. It's both humbling and oddly comforting, knowing the universe makes beauty for no audience at all. Light joke number 3 arrives on a slow current. If you tried to mine these diamonds, by the time you reached them, you'd probably have invented 5 new ways to define futile. You linger here for a moment longer, watching the unseen rain continue its endless fall, each crystal a tiny miracle of pressure and patience. Above, the storms keep feeding this river of carbon. Below, the fate of each diamond is written in heat, and here you are, suspended between them, an audience of one, for a show that's been running for billions of years. You hover in a layer of atmosphere so dense it almost feels like a fluid, the kind you could swim through if you had lungs made for such a place. The diamond crystals, now fully formed, slip past you in slow, deliberate streams. They don't tumble chaotically, they glide, each one following a path carved by gravity's steady hand. If you squint, you can imagine them as invisible rivers, flowing ever downward toward depths no sunlight will ever touch. The mainstream fact emerges gently. Deep within Uranus and Neptune, scientists believe that the combination of heat, pressure, and gravity organizes the movement of materials into convection currents. These are slow, looping flows that carry energy and matter through the atmosphere and mantle, much like the slow churning of water in a pot just before it boils. In this case, the water is a superheated mix of hydrogen, helium, and other compounds, and the spices drifting through it are tiny diamonds. Quirky thought, if the upper atmosphere is the birthplace, this is the lazy river ride for the newborn gems. They drift along in currents that may take years, even centuries, to complete a single circuit. No hurry here. If a diamond had a personality, you'd expect it to be patient after all. It took billions of years to even form. Scientists still argue about what happens to these diamonds in the deepest parts of the planet. Some propose they eventually sink to form a vast diamond layer around the core, a glittering shell of solid carbon. Others suspect they may melt back into carbon-rich fluids under extreme temperatures, dissolving into the next phase of the planet's chemical story. The truth is hidden far beyond our reach, where our instruments can't yet follow. The light here is almost non-existent, but you can sense the diamonds by their movement. They alter the flow around them, like stones dropped in honey. You imagine reaching out to touch one, it would feel impossibly smooth, warmed by the planet's heat, yet solid in a way few things in the universe are. Callback moment. Remember when we talked about carbon planets earlier? If one of those worlds exists, this diamond rain might not stop at the mantle. It might run all the way down to a diamond core, a place where the concept of solid ground would mean an endless crystal plane beneath your feet. Light joke number 1 drifts in. Somewhere, there's a geologist dreaming of this place, only to wake up disappointed that the biggest diamond they've ever held could fit in a coffee cup. As you float alongside the current, you catch sight of something stranger eddies in the flow, tiny whirlpools where diamonds cluster before spiraling downward again. It's mesmerizing, like watching galaxies form in miniature. The diamonds collide, separate and continue on, each bound to its own gravitational path. Scientists still wonder how these rivers of diamonds affect the planet's magnetic fields. Uranus and Neptune both have magnetic fields that are oddly tilted and off-center compared to Earth's. And some researchers speculate that conductive layers deep inside, possibly influenced by diamond rain, play a role in shaping those fields. If true, it would mean that the weather here doesn't just shape the surface. It might help shape the very space environment around the planet. Light joke number 2 sparkles faintly. If you had a spaceboat, you could just float along these diamond currents, waving politely to each crystal as it glides past, though you'd have to pack about 1,000 lifetimes worth of snacks for the trip. The silence down here is profound, not the absence of sound, but the presence of something bigger than sound. Pressure, heat, and time all have their own music, and it's playing on a frequency you feel more than hear. The diamonds move in sync with that rhythm, as if they know they are part of something ancient and inevitable. Light joke number 3 drifts lazily along. You could spend an eternity here, and still never see the same diamond twice, not because they're all unique, but because you'd be too relaxed to keep track. The invisible rivers keep flowing, hour after hour, century after century, long after you drift back toward the higher layers. They are the final act of the storm above, carrying its creations into the hidden heart of the planet. And as you rise, you can't help but feel a little envious of the diamonds. They have the patience of worlds, and a journey without hurry. You let the drift slow until you're barely moving, buoyed by warmth and patience in a place that feels older than memory. Somewhere above, lightning is still whispering carbon loose. Somewhere below, invisible rivers are still guiding crystals home. Between those layers, in this hushed middle country, a mischievous thought arrives and sits cross-legged beside you. If weather can be diamond, and oceans can be molten carbon, what might life look like here, if it looks like anything at all? The mainstream fact clears its throat gently. Life as we understand it on Earth leans on liquid water, a modest temperature window, and complex carbon chemistry taking place in a solvent that lets molecules mingle, react, and self-replicate. That recipe has worked spectacularly well for a few billion years on our small blue rock. Down here, the pantry is different. Pressure that would crumple steel into origami, heat that makes Venus blush, solvents that aren't water at all. By terrestrial standards, this is a nope zone. But you're not filing a visa application. You're letting imagination clock in for the night shift. So you ask a quieter question. Could patterns that harvest energy, maintain structure, and adapt exist in these conditions? If they could, they might not be cells in the familiar sense. They might be networks, films, lattices, systems that use pressure, heat gradients, and electric fields the way pond life uses sunlight and nutrients. A quirky picture coalesces like frost on cool glass. Imagine a carbon lace anchored along a boundary where solid diamond meets conductive melt, a flexible scaffold threaded with impurities boron here, nitrogen there that give it just enough electrical personality to shiver when currents pass. The lattice breathes by routing charge through itself, pulling energy from tiny differences in temperature or ion flow, repairing breaks by recruiting stray carbon from the passing soup. You wouldn't see it wiggle. You'd notice it persist, the way a candle flame persists while molecules race in and out. If that sounds suspiciously like life, that's the point of the thought experiment. Scientists still argue whether such exotic life is plausible without water as a solvent. One camp says, chemistry needs a medium where molecules can meet easily, and nothing beats water for that. Another points to superionic phases like water under extreme pressure, where hydrogen ions wander through an oxygen lattice as possible playgrounds for charge-based information processing. A third says, gently, we have one biosphere sample size. Our confidence should wear slippers. You nod at that last line. Slippers are absolutely the dress code tonight. You turn the camera of your mind to the Diamond Expressway you rode earlier, the ceaseless fall of crystals through layers of changing density. What if some regions along that highway are reefs of sorts textures, where falling diamonds tend to snag briefly, concentrate, and then move on? Those snag points could seed structure, a place for that carbon lace to anchor, harvest a little energy from the passing traffic, embolden its own pattern by templating new growth. On Earth, coral polyps borrow carbonate from seawater to build reefs. Here, the polyp borrows charge and carbon from a storm-fed stream. Light joke number 1 taps politely. If you tried to interview this reef, you'd get no quotes, only conductivity graphs. I'd like to thank the gradients for their unwavering support. You listen for the music of the place, because life, at minimum, needs a rhythm to ride day, night cycles, seasons, tides. Do such rhythms exist here? The mainstream answer is yes, just slower or stranger. There are convective pulses, gravity waves, and storm cycles that wax and wane. Even without sunlight reaching these depths, heat flux from below and storm feeding from above could beat a metronome. A system that can tune itself to those pulses might encode a primitive memory, grow this way when the flux rises, that way when it falls, strengthen links that carry charge efficiently, prune ones that don't. Does that start to sound like learning? You let the word sit without raising its voice. Scientists still argue whether information storage needs discrete molecules, shuttling around RNA, proteins, that whole Earth kit, or whether field patterns, stable charge distributions, resonant circuits and conductive matrices could stand in as memory. The lab crowd says, show me a replicator, the theorists counter. Show me a stable pattern that biases its own continuation. The planets, gracious hosts that they are, provide no clarifying footnotes tonight. A callback drifts by wearing a lifeguard whistle. Remember the molten diamond spar? If any organism lives near that sea, it must make peace with phase boundaries. Perhaps it survives by surfing the interface, where solid meets liquid and gradients are strongest. It expands when the melt cools and contracts when it warms, its very shape a ledger of thermal history. That ledger creases, kinks, and preferred pathways could be its genome, copied when a fracture splits the lattice, and each half regrows along the same habits. No nucleotides, just habits that inherit. Light joke number 2 yawns. If natural selection happens here, the winning trait is most chill about being squeezed. Not glamorous, very effective. You let the idea rise toward gentler layers. Could there be aerosol ecologies higher up charged clusters that assemble in lightning-rich regions, temporarily stabilizing by stealing electrons from their neighbors, then drifting apart like sleepy starlings? Not life, perhaps, but pre-life patterning, chemistry rehearsing for a concert it may never play. On Titan, in Saturn's kingdom, complex hydrocarbons self-assemble into haze. On these giants, similar photochemistry and electrochemistry might sculpt filigrees that make the leap from pretty to informationally stubborn. Scientists still argue whether polyaromatic hydrocarbons and other soot precursors in these atmospheres can achieve templated growth, the molecular equivalent of copy that shape. Even if they can, does anything in this hammer-gentle, squeeze-loud environment give them the time and shelter to take the next steps? The pessimists say the pressure gradient shreds subtlety. Optimists answer that gradients also pay the bills, and every biosphere is a clever accountant. Light joke number 3 arrives on tiptoe. If an astrobiologist ever files expense reports from Uranus, line item 1 will read, bought a better definition of alive, approved without comment. You take a last, patient scan of the scene, a boundary reef of carbon lace quietly rerouting charge, diamond drifts that serve as scaffolds and supply lines, melt lanes that erase and write in alternating bars, eddies that gather and scatter building blocks like tide pools feeding ashore. You notice how many of these features repeat fractals of habit nested at different scales. On Earth, life loves fractals. Alveoli in lungs, mycelium in soil, veins in leaves. If habit truly can inherit here, then perhaps the planet's interior is already practicing the art of staying the same while changing. The mainstream caution steps in, friendly but firm. None of this is evidence. It's a bedtime model, a way to keep curiosity comfortable while the data catch up. Our only confirmed biosphere still basks in sunlight and swims in water. These diamond depths offer physics that cooperates with pattern, not proof that pattern has crossed the finish line into life. Scientists still argue whether we should even use the L word outside Earth without new categories life, proto-life, active matter that signal humility. Your vote tonight is for kindness. Let the definitions stretch later. For now, enjoy the possibility that the universe may have more than one way to hum a self-sustaining tune. A soft callback rounds the corner the weather app for Neptune you joked about. You flick it open in your mind, calm with a chance of bedazzlement. Interior advisory, possible structured conductivity along diamond interfaces, motorists, that is to say, atoms, expect delays. You snort once, quietly, and the sound disappears into the pressure like a pebble into honey. You angle yourself gently toward the next layer, where questions gather like mist. If there is life here, or something that rhymes with life, it will likely ignore our categories and flourish by its own bookkeeping. If there isn't, that's fine too. The place is already brimming with pattern. Either way, the diamonds keep falling, the rivers keep flowing, and the gradients keep paying the energy bills on time. You start to rise, slippers definitely still on, letting the scene shrink until it's an elegant diagram tucked between 2 pages of night. Ahead waits a softer room full of question marks, the part where we set the fanciful sketches next to the careful data and see which edges touch. The science stays slow, the galaxy stays wide, and somewhere beneath you, if any lattice is listening, it goes on arranging itself with exquisite calm. You drift upward, but not quickly. The ride is slow enough that thoughts can keep pace, settling beside you like quiet passengers in a midnight train car. Somewhere above, starlight you'll never see, filters down through countless layers. Somewhere below, diamond rivers you've left behind continue their silent work. Between those two extremes lies the stretch where questions hang like lanterns, swaying with the gentle motion of curiosity. The mainstream fact greets you first, polite as ever. Science thrives on incomplete maps. Every planetary model we've built, whether for Jupiter, Saturn, Uranus, or Neptune, still wears patches marked, "Here be uncertainties." That's not a flaw, it's a feature. It's the empty spaces on those maps that invite new expeditions, new instruments, and, yes, new bedtime stories. One of the biggest question marks glows faintly. How far does the diamond rain actually fall? We know the pressures and temperatures in certain planetary layers could, in theory, squeeze carbon into diamond. But does that diamond stay suspended for a while, glittering in mid-depth currents, or does it immediately begin its slow descent toward the core? Some models suggest a diamond hailstorm zone, where crystals are constantly forming, falling, and being replenished by fresh carbon from above. Others propose a one-way trip once formed. The diamonds drop without pause, vanishing into deeper darkness we can only guess about. Scientists still argue whether these two scenarios are mutually exclusive. Could there be multiple rain bands layers where diamonds form, dissolve and form again, like repeating weather patterns stacked on top of each other? In a storm this alien, nature might be running several different recipes at once. A quirky little question floats by, wearing oversized glasses. What shapes do these diamonds take? On Earth, slow cooling can give us perfect symmetrical crystals. In these giant planets, the journey from gaseous carbon to solid diamond happens under constant turbulence, with lightning storms above and molten rivers below. Do the crystals end up jagged and irregular, like shattered glass? Or do they become rounded, polished smooth by pressure and time, like pebbles in a stream? If they're small enough, microscopic, even they might behave more like dust than gems, scattering light in strange pearly ways. Light joke number 1 shows up with a wink. Somewhere in the galaxy there's probably a word for raindrop-shaped diamond, and it's probably unpronounceable without a pressure suit. Another question shuffles forward. How much carbon is there to work with in the first place? This isn't idle curiosity, it's about whether diamond rain is a rare novelty or an endless downpour. Planetary formation models tell us that Uranus and Neptune likely contain significant carbon in their ices and gases, but the distribution matters. Too deep, and the carbon never gets a chance to crystallize. Too shallow, and it escapes before the magic happens. Right now, our best estimates are stitched together from a mix of telescope data, spacecraft flybys, and computer simulations. That's a bit like trying to reconstruct a recipe from the smell alone. Scientists still argue whether future orbiter missions could carry instruments sensitive enough to detect these deep processes indirectly, perhaps by measuring gravitational anomalies caused by layers of different densities. If those anomalies matched what diamond-heavy layers should look like, we'd have stronger evidence that the rain is real. Until then, the debate remains a polite tug-of-war between theory and observation. Then there's the mystery of timing. Are we imagining a planet where diamond rain is happening constantly, a steady glitter fall that's been going on for billions of years? Or is it more like a seasonal event, triggered by slow cycles in the planet's interior? On Earth, volcanoes sometimes stay dormant for centuries before erupting in spectacular fashion. Could diamond rain follow a similar rhythm, with long quiet spells interrupted by sudden storms of crystallized carbon? If so, we'd have to be very lucky or very patient to catch one in progress. Light joke number 2 sidles in. If your weather forecast says, diamond rain likely in 3,000 years, it's probably safe to leave your umbrella at home for now. And then comes the question that's been humming softly since the start of this journey. What would it actually look like? Not the diagrams in textbooks, not the simulations on a supercomputer, but the real thing, the sky dark and dense, lit from within by lightning, with countless points of hard, refracted light tumbling slowly downward. Would it look like snowfall in reverse, bright against a darker background, or like sinking through a champagne glass where every bubble is a jewel? Your mind tries to paint it, but the canvas keeps spilling into 3 dimensions. Scientists still argue whether such imagery is too romantic for real planetary science. But here's the secret. Even the most disciplined researcher has, at some point, let themselves imagine the scene. That's because questions aren't just data gaps. They're little bridges between what we know and what we long to witness. A callback slips in from earlier. Remember the molten gem oceans you pictured? The unanswered questions about them are just as enticing. How deep are they? Are they smooth like mirrors, or choppy like storm seas? Do they glow faintly from the heat, or are they invisible in the dark? And if a diamond falls into one, does it melt quietly or explode into 1,000 glittering fragments? Light joke number 3 leans on the doorway. If diamonds do shatter when they hit, then somewhere deep inside Neptune there's a beach made entirely of glitter. Sunglasses optional, but only if you can stand the pressure. You realize the questions aren't shrinking as you rise, they're multiplying, branching like the conductive lattices you imagined in earlier layers. And that's the nature of this kind of science. Each answer you find is really just a neat little box containing a handful of smaller, shinier questions. Above, the atmosphere is thinning. You're almost at the edge of where this planet's secrets can reach you. But before the next phase of the journey, you pause, letting these unanswered riddles glow softly around you like constellations. Some will be solved in your lifetime, others will keep twinkling long after. Either way, they're part of the same sky, the one that lets curiosity and comfort share the same seat. You take a slow breath, ready to let the final descent carry you somewhere quieter still. Ahead is the part where questions fade into calm, where curiosity and rest can finally shake hands. You're still hovering at the upper reaches of the planet's atmosphere, just far enough that the diamond rain below has faded into memory, but not so far that the planet's presence has let you go. Its pull is still there, a soft, steady tug that feels less like gravity and more like a hand at your back, guiding you toward the exit. The mainstream fact is almost shy about appearing now. Every exploration, whether by spacecraft or imagination, has to end somewhere. Voyager 2, the only spacecraft to have ever visited Uranus and Neptune, spent mere hours in their vicinity before racing on into the dark. In that short time, it sent back glimpses of swirling clouds, tilted magnetic fields, and hints of the mysteries we've been drifting through tonight. That was decades ago, and no one has been back since. The data we have is precious, but incomplete, like a half-finished lullaby. Quirky thought floats in, slow as a falling feather. Maybe the diamond rain is still going on down there, unchanged since the day Voyager passed by. Maybe it will still be happening a billion years from now, when the stars themselves look different. These planets are not in a hurry, and they don't mind if you come back later, much later. Scientists still argue whether our next mission here should be a fast flyby again, or a long-term orbital stay. The former is cheaper, but the latter might finally let us see those invisible rivers of diamonds, map their depths, and understand the strange weather patterns that shape them. Until then, all we have is the quiet, shared imagining we've been building together tonight. Light joke number 1 tiptoes in. If NASA does send another mission, they might want to pack a planetary-sized engagement ring, just in case the diamond rain takes offense at all the curiosity. Up here, you can see how small the whole scene is against the backdrop of space. The planet hangs like a jewel itself, pale blue and streaked with shadow. Somewhere beyond it, galaxies swirl in patterns that make even diamond rivers seem small, and yet, in the quiet way of such things, both the vast and the tiny feel equally worth wondering about. The callback moment you remember the first time we dipped into this atmosphere, the lightning storms, the carbon transforming under pressure, the molten gem oceans. All of it is still there, still happening, whether you're here to witness it or not. That's the comfort and the ache of space. The story goes on without you, but you get to carry a piece of it with you. Light joke number 2 wanders by. If you ever do manage to scoop up a handful of diamonds from down there, try not to lose them in your couch cushions back home. You take one last look at the horizon. It's not really a horizon here, more a gradient, fading from the soft blues of the planet's upper clouds into the deep black of interstellar night. Somewhere in that in-between, the noise of thought has slowed to a whisper. The curiosity is still here, but it's wearing slippers now. Light joke number 3. Maybe curiosity isn't a cat. After all, maybe it's a drowsy astronomer. Notebook in hand, drifting off mid-sentence. You let yourself lean into the slow drift away from the planet, feeling the gentle release of its pull. Each kilometer you gain makes the air thinner, the light sharper, and your mind quieter. Soon, the diamond rain is just an idea again, one that might visit you in a dream later tonight. And now, the wind down begins. The planet is far behind you now, but its presence lingers in the softest ways, like the faint glow you see after staring at something bright, or the echo of a song you've just heard. The darkness of space isn't empty here. It's filled with quiet layers, like blankets stacked one over the other. Each one muffles the noise of thought a little more. Your breathing has matched the rhythm of the drift. In, as if you're drawing in the calm of 1 billion kilometers of space. Out, as if you're letting go of every thought that tried to follow you here. The stars are unblinking, but you don't feel watched. You feel kept, held in place by the same gravity that holds planets to their stars, stars to their galaxies, and galaxies in the slow dance of the universe. If you picture the diamond rain now, it's not as something rushing or chaotic. It's a soft, patient cascade, happening on a timescale too vast to measure. Each crystal finds its place without urgency, without resistance. You can imagine yourself as one of them, carried by currents you don't have to control, heading exactly where you're meant to go. The questions we left behind still glow somewhere deep in the planet, but they're not calling you tonight. They can wait. Out here, there's no clock, no deadline, only the steady hum of the cosmos, the faint, almost imperceptible vibration of existence itself. You could stay here as long as you like. No hurry to return, no rush to understand everything at once. Just the comfort of knowing that wonder doesn't vanish when you close your eyes. It's still there, still raining diamonds, still waiting for you whenever you drift back. Sweet dreams.